So hello everyone, welcome to our AIMEDx webinar series. My name is Hongliang Xin. I'm professor of chemical engineering at Virginia Tech. So this is my great pleasure to introduce our speaker today, Keqiang. Keqiang is a PhD candidate in computer science at Texas A&M, working on scientific machine learning and AI for science. His work spans geometric deep learning and large language models for application in material science, protein science, and drug discovery. His work has been published in premier venues, including NeurIPS, ICML, ICLR, and many others. He has been recognized with a D.E. Shaw Research Doctoral and Postdoc Fellowship. Keqiang has contributed to open source projects, including DIG and X and AIRS, very popular libraries at GitHub. And he achieved top performance in open challenges, including the Open Catalyst Challenge and MathBench Challenge. Today, he will be talking about AI for material discovery, graphs, language models, and agents. So Keqiang, thank you very much for joining us today. So the virtual podium is yours.
Yeah, thank you very much for Dr. Xin's introduction. I'm Keqiang Yan, a PhD candidate from Texas A&M. I conduct research in scientific machine learning and AI for science. Today, I will majorly talk about AI for materials discovery, covering topics in graphs, language models, and agents. Yeah, let's get started. So before we talk about AI for science, let's begin from science. What is science? Science is mostly about understanding the world around us. It covers different topics and time and length scales, from the smallest quantum mechanism to the middle level atomic systems like materials, proteins, molecules, and to larger ones like fluid dynamics, and even larger ones like atmosphere, aerospace, and others. So why should we do AI for science? Here I borrow a famous saying from Dirac back in 1929. Due to the discovery of Schrödinger equation, actually a large part of physics and the whole chemistry are completely known for the underlying laws. But there is a remaining and huge challenge to apply this kind of Schrödinger equation to solve realistic systems because of the complexity. According to the equation, we can say that it models the interaction between electrons and electrons. And the complexity of Schrödinger equation is actually with the exponential relationship with number of electrons in the system. And it is infeasible to solve for larger systems, even with the help with most advanced supercomputers. For sure, there are some algorithms try to speed up the calculation of Schrödinger equations, like density functional theory-based algorithms, but they still have exponential complexity with the relationship with number of electrons in the system. And that's why we need AI for science. Here I borrow like a statement from Microsoft Research about the fifth paradigm of scientific discovery. The fifth paradigm will be about developing AI methods to accelerate our understanding of science and help us to design better engineering systems. So let's again look at the complexity of scientific discoveries. Here, for example, the stable drug-like molecules that potentially can be discovered actually has the number of 10 with the power of 60. This number is actually larger than the number of atoms in the solar system. And again, if we look at the stable material structures, the number is even larger, with 10 with the power of 180. To understand the scale of this number, it is roughly the square of number of atoms in the observable universe. So because of this super large exploration space, if we use the Schrödinger equation or density functional theory that are super complex, it is impossible to go through all these candidates. These numbers are actually too large to even count. And that's why we need AI for science, because AI algorithms can provide a significant speed up over density functional theory and other traditional methods for the scientific discoveries. And actually, it can bring like years of discovery to days. Here, let us do like a demonstration of the discovery pipeline using AI or using traditional methods. For the discovery of novel materials, we begin from desired properties and then ask experts to draw some candidates for some experimental verifications and computational ones. But all these verifications will take days to weeks or even months to years for a single candidate. However, like I show here, with the AI algorithms proposed by us, we can predict the physical properties of given candidates within milliseconds. With this being said, more than 10,000 candidates can be screened within a single day with a single GPU. And that's why we need AI for science. Additionally speaking, the reason that we can replace density functional theory calculations with AI algorithms is because of the accuracy. When comparing with density functional theory calculations with experimental verifications, the error range is around 0.1 EV per atom for the energy. And for the error between our developed AI algorithms and the density functional theory ground truth, we can achieve around 0.006 error. With this comparison, we can see that if we directly replace density functional theory with AI algorithms, we are only adding a small variance to the density functional theory predictions, but bringing more than 5 magnitude speed up for the traditional methods. And secondly speaking, the reason that we develop AI for science algorithms is because we want to provide different perspectives in scientific discoveries. The traditional discovery relies heavily on human intuitions because of the cost of computational and experimental verifications. With that being said, people more like rely on human intuitions, and they can only do like limited number of explorations, and the searching space will be hugely limited. But with AI like speeding up, we can actually support brute force searching for the whole space, and because of the time and the money efficiency of AI algorithms, this can support sort of unbounded searching freedom due to efficiency. And this will open a new door for scientific discoveries beyond human intuition and thinking process. And here is like overview of our past research. We use AI to speed up scientific discoveries and then use science rules like group theory, equivariance, symmetry to provide guidance for AI method development. We not only do prediction, but also do generation. For the prediction, we can do scalar ones like formation energy, band gap. For the tensor ones, we can do dielectric tensors, piezoelectric tensors, and elastic tensors, and even general tensors. For the generation, we can begin from desired properties and directly do the inverse design to generate candidates with desired properties. And the reason that I use science to guide AI is because we want the AI algorithm to be robust, and we want it to like use scientific rules to significantly reduce the searching space. For sure, like I mentioned before, the searching space for the potential like discoverable like drug-like molecules and stable materials are super large. And if you do not use science, there are other like biases you need to deal with data augmentation. For example, for a given molecule, people record the structure with coordinates, and if you directly use coordinates as the AI input, a single structure can have infinite number of coordinated descriptions, and the exploration space will be like even larger for the AI method. And we also want AI algorithms to satisfy physics rules and laws, and it will be like data efficient for the learning. This is more like stand on the shoulder of human knowledge to find solutions for AI. And there are like several works in past years published by us in materials, molecules, and proteins. Here I marked some projects led by me, by Orange, and we established a lot of collaboration with outer institutes, universities, and companies. And today I will talk about AI for materials discovery, covering graphs, language models, and some ongoing work on agents and others. For the graphs, I will talk about invariance, equivalence, and completeness, and how to achieve these physical pairs. And then I will move forward to more complex general tensor predictions. For the language model, I will talk about generation. And by these bullets, we today will cover a complete AI toolset for crystalline materials discovery, including prediction, generation, and agents. Not only for scalars prediction, but also for general tensors and also for dynamics simulations. So let's begin with the crystalline materials we are dealing with. The crystal structures can be represented by three matrices, including one, the lattice matrix, to represent the periodic patterns of the minimum unit cell, which is the minimum unit in the crystal structure. And we also need the atom matrix and atom position matrix to mark the atomic numbers of every atom in the cell, and also the coordinates of every atom in the cell. So the reason that we care a lot about representations is because it is the bridge between real-world 3D objects and the AI algorithms. And honestly speaking, the AI algorithms can only understand and comprehend and consider information captured in representations. Let's begin from the previous widely used multi-edge crystal graph proposed by CGCNN. As we can see, for sure, it can capture the local interactions within a radius for this given light blue node, but it only considers bond lengths and neighboring atomic type information, and it is not complete and have a lot of limitations. From our side, we actually want to build representations to be powerful, robust, and equivalent. The first thing we want to achieve is about completeness. We want to make sure the AI algorithms can distinguish any different structures and do not map different structures to the same representation, which is totally wrong. Here, I show two cases that a previous multi-edge crystal graph will fail to distinguish. As we can see on the upper part, on the left hand and right hand side, there are totally different structures, but the graph will be the same. And similarly speaking, on the below part, these two structures are different, but the graph is the same, and the property prediction will be identical, which is wrong. And additionally speaking, we want to achieve equivalence. If we rotate the structure, for sure we want the force predictions to be rotated accordingly. And even for tensors, if we rotate the structure, the tensor predictions will need to be adjusted accordingly. And we also care about equivalence. Here I show several different unit cell structures for the same crystal. For sure, their unit cell mathematical descriptions will be slightly different by shifting the periodic boundaries or rotate the periodic boundaries or changing the periodic patterns to another set without changing the volume. But all of these describe the same structure and should have the same representation. Let's begin from the first task about property prediction. For this task, we are given 3D crystal structures as input, and we want the AI algorithm to predict physical properties like formation energy, band gap, atomic forces, and even more complex ones like dielectric tensors, piezoelectric tensors, like I show on the right-hand side. These are the piezoelectric tensors with relationship with crystal classes. There are several challenges not addressed by previous works. mainly physical pairs should be considered by AI algorithms when doing this task. Firstly, is like invariance, like I described before. For sure, there are different mathematical descriptions for the same structure that can be used, as I showed below, A, B, C, D, different unit cell structures for the same crystal. But they should have the same property, and this is a so-called invariance. And for equivariance, if we rotate the structure, we want the atomic forces to be rotated accordingly. And for the dielectric tensors, they should change accordingly. And thirdly, we care about completeness. We want the AI model to be robust and can distinguish any different structures. And the question is how to achieve these three together. Let's first talk about invariance. In our NeurIPS paper in 2022, we defined the physical pairs, mainly invariance that should be considered and satisfied by crystal representations. First is about unit cell E3 invariance. It means if we rotate or reflect the periodic patterns and the atomic position matrix together, or translate the atomic position matrix alone, the structure will not change and the representation will not change. And additionally speaking, as we show here, another invariance about periodic invariance. In A and B, these are like identical structure, but they can have a different unit cell structures by slightly shifting the periodic boundaries from P1 to P2. For sure, they have a dramatically different inner cell structure, but they should have the same representation. And there are some insights we can share to achieve this kind of invariance. We first need to treat a given atom and all its periodic duplicates as a single node in the graph representation. And we need to consider all interactions as multi-edges and consider the interactions as a radius. Let's first look at when the first bullet is broken. Here I show the graph representation used by OC team for their OC20 challenge. They construct graphs using radius and consider all the neighboring unit cell atoms within the radius as single nodes. However, like we can see here, if you consider the blue nodes and its duplicates as individual atoms or individual nodes in the graph, we can get 3 nodes on the left-hand side for the blue atom and 2 nodes on the right-hand side. This will break the invariance, and you can generate a totally different graphs for the same structure. And here I show a case that satisfies all the invariance by considering the local environment. The insight is that the cell boundaries are artificial, defined by human being to describe the periodic structure, but the local environment will never change for whatever mathematical descriptions you use. And additionally speaking, we care about completeness. The reason that we care about completeness is because we want the AI method to be able to distinguish any different structures and capture the geometric information with no information loss. And ideally speaking, the representation should be able to fully reconstruct the 3D structures from the representations. Then how to achieve this kind of completeness? There are several insights I can share here. We first achieve the local completeness by using the insight that periodic patterns for every atom in the same structure are the same. And by using the periodic patterns, we construct a local coordinated system for every node I. Like I show here, II1, II2, and II3. This will be 3 lattice vectors. And then any neighboring node, the position of any neighboring node can be uniquely determined by using 3 relative angles, like I show here, JII1, JII2, and JII3, and also the distance JI. And similarly speaking, the position of J can also be uniquely determined by a vector JI. And then the question will be how we can extend this kind of local completeness to global one. way we can achieve that is also like straightforward. We can do this by lattice frame alignment. Like I mentioned before, periodic patterns are the same for every atom across the structure. And as we can see from step 3, after we reconstruct the local environment for node I or the gray node, we can extend the local completeness from the gray node to the purple one by aligning the X, Y, Z coordinates or like vectors of the J frame. And that's why we can achieve the global completeness. And then using these insights, we build the graph representations that are complete using the atomic numbers as node features and distance plus 3 lattice angles as edge features, or using the vector EIJ, EGI to build the equivalent graph representations. We prove the completeness of these representations with rigorous mathematical proofs. Here are some impressive facts about the model design that I want to share. We actually achieve the linear complexity with the number of atoms in the cell. And here C means a constant around 20, and then N is the number of atoms in the unit cell. The architecture we support, including invariant and equivalent ones, for the prediction of scalars and forces and others. We achieved a lot of good results using the proposed conformer. We achieved the state-of-the-art foundation model from academia on MathBench discovery. We achieved the linear complexity in terms of system size and much faster than foundation models developed by Meta and Microsoft Research. As we can see in the table, we achieved the state-of-the-art MathBench discovery evaluations in terms of RMSE, R-square, and others by comparing with other foundation models like famous one, Maze, 7net, Orbital Materials, or Meta Equiformer version 2. And we are much faster, like 2 to 3 times faster than Equiformer version 2 and 7net. And this kind of foundation model can be directly used to predict a wide range of physical properties without even fine-tuning. There are a lot of societal impact for this line of research, like for energy, clean energy, for energy sustainability, for environmental sustainability, like the materials for carbon capture, for healthcare applications, industrial applications, and others. One thing I want to mention is about the comparison between other foundation model teams and our team. Our team are like lead by me and finished by like 2 of my undergrad mentees. And for other teams, they are supported by a huge amount of money, like this Optimal Materials. They raised more than 20 million and have a lot of staff. And other teams like Meta, Microsoft Research, Google, DeepMind. And for the foundation model design, we design the model to predict energy, force, and stress. It can be directly used for dynamics simulations to relax the unstable structures from to stable ones, and it can also be used to predict phase diagrams, phonobond structure, and bulk modulus. Now here I show a demo about our model predictions to relax unstable structure to the stable one, like we can see from this video. And additionally speaking, our model can predict accurate phonobond structures compared with density functional theory calculations. As we show in this table, we can see that we actually achieved significantly better performances than other foundation models. And the reason that we care about phonobond structures is because phonons are the main carrier of heat in like materials. It is important for the discovery of semiconductors and to evaluate the stability, and also for other applications like transistors, LEDs, and quantum devices. The reason that we can directly predict phonobond structures is because the phonobond structure can be derived from force predictions by physics rules. And the figure shows the relationship between positions in reciprocal space, where the points on x-axis represents important high symmetry points. And the reason that every x can have several y values is because there are multiple frequencies for a given structure, because atoms can vibrate differently. If you want to understand, this is more like if you shake a stick, every position on the stick will have a different frequency. And similarly speaking, every atom in the structure can have a different frequency. There are other material discovery applications that I will not go into details, like phase diagram prediction for alloy discovery, bulk prediction, and various dynamics simulations, and so on. Then let's move forward to general tensor property prediction. For this task, we care about how to predict high tensor order properties like order 2, dielectric, order 3, piezo, order 4, elastic. And we also care about how to guarantee the underlying physics constraints like equivariance and the space group constraints are faithfully satisfied. So here I show the relationship between like the freedom of tensor properties with the relationship of symmetry in the crystal structures. For example, the cubic structure has the highest level of symmetry, which means if you reflect the structure by YZ plane or XZ plane, or if you rotate the structure by 90 degrees, it will map back to itself. But for other systems like triclinic, there is no symmetry at all, and whatever transformation you apply to the structure, it cannot map back to itself. And this kind of symmetry will actually influence the freedom of. Yeah, I see several questions. The first is about mostly in graphs we're able to capture local interactions, and that's great. However, in cases where equivariance is involved, how can long-range interactions be captured effectively at a less computational cost? Yeah, this is a great question, and a quick answer to this will be the long-range interactions can be captured by several layers of local information aggregation. And that will be efficient. And if you want to consider long range in a single layer, it will be computationally expensive. For another question, if a generative AI model is used to obtain graphical representation of new materials, is it possible to inversely predict their structure CIF files? Yeah, this is another great question, and actually we'll cover how we achieve this in our generative AI in the second part. So wait a bit till I answer this. So let's go into a little bit about the dielectric tensors. The dielectric tensor describes how a material responds to an altered electrical field in different directions. The reason that there are responses in the material structure is because if you apply an altered electrical field, the electrons and the atomic nucleus will shift in different directions and causing some inner electrical piezo polarization in the material. And if the material structure is anisotropic, the dielectric responses will depend on directions. For example, if we apply an electrical influence in the x direction, there will be 3 responses in the structure, dx, dy, dz, where d is displacement. And to describe the whole response, we will need 9 values in the matrix to represent the dielectric tensor. And the reason that it is important is because there are a lot of applications that relies on the dielectric tensor predictions for capacitors, for semiconductor devices, and even for optical ones, energy storage, and others. The first thing, the first major challenge for predicting tensors will be the equivariance. Here, as I show here, if we rotate the material structure, the dielectric tensors and other high-order tensors will rotate in a complex way. Not only the direction, but also the shape will change. However, they actually have a rather simple mathematical relationship. If you rotate the structure by r, the dielectric will rotate in this equation, and the piezo will rotate in this equation. And generally speaking, general machine learning models are developed for prediction of scalars, for classifications, but not for prediction of matrix form tensors. And for general tensors with order n, actually the shape will be 3 with power of n. And we also care about space group constraints because, as I showed before, the symmetry of the structure will influence the freedom in tensor values. Here I show an example of rotation of 19 degree and for the dielectric tensors. For example, the rotation matrix by 90 degree can be represented by as this. And due to the equivariance, I mentioned before, if the structure has this kind of equivariance, then the left-hand side will equal to the right-hand side for this R1. And by using this equation, we can directly get the xz entry will equals to minus yz, where yz will equals to xz, and in the end, xz will equals to minus xz. And with this being said, xz will equals to 0. And similarly speaking, there will be some equal entries like this one, and opposite entries like this one and this one. So in short, space group will result in strictly 0 and equal entries in dielectric tensors, and that's why it's important. To deal with these challenges, we propose the general materials tensor network. It is carefully designed to satisfy all symmetry constraints for general tensors, not only for dielectric, but also for piezo and elastic. We achieve this by 3 design components, including the symmetry-informed crystal graph representations, and also the message passing, and also the prediction block. We make sure that the crystal symmetries are satisfied in every block at different levels, including the atomic level and the crystal levels. For the atomic level, there are requirements for its features because if 2 atoms can be mapped to each other by the symmetry, it means they must have identical invariant features and rotated or reflected equivalent features. This is natural. For example, for this atom on the left-hand side and this atom on the right-hand side, they have a reflection symmetry, and the invariant features should be the same, and the equivalent features should also be reflected. And additionally speaking, for the crystal level features, there are some requirements because according to the Newman's principle, crystal features should retain the same spatial symmetry as the structure. And if you rotate the structure, it is the same structure. Then if you rotate the representation by the same transformation, the representation should also remain the same. And by achieving this kind of requirements at different blocks, at different levels, we mathematically prove we extract crystal features invariant to all the space group transformations. And to predict the matrix form complex tensors, instead of directly forming this kind of matrix or tensor, we mimic the physical response of these tensors they describe and use the gradient to directly obtain the matrix form. And this is more like favorable because directly restricting the output to satisfy the equivalency is hard, but predicting some dielectric electrical displacement field like vector D is relatively easy. And by taking the outer electric field E as a conditional input, the dielectric tensor can be directly obtained by the gradient. I will not go into too much details of these equations, and here we show the results. We achieved 100 success rate in satisfying all symmetry constraints, while previous works can only achieve 0 or limited less than 10%. And we also achieved the state-of-the-art Frobden's norm, which is a matrix favorable for evaluating the difference between matrices. Here, I also show some visual demonstrations to show that our predictions satisfy all the spatial like properties of these piezoelectric tensors and dielectric tensors, elastic tensors. There are a lot of social impact in this line of research for the discovery of capacitors, sensors, and others, even aerospace and construction industries. And then I will move forward to the generative AI. So using the previous methods, we already have AI methods that predict scalars, tensors, and even dynamics. It can support the forward discovery, which is searching based. But what is next? We also need the inverse design. By using the inverse design, we can directly let AI methods to propose candidates with desired properties, and there is no searching needed. The reason that we use language models as our generative AI backbone is because language models have the richest amount of human knowledge beyond any living human. And they have been verified to capture the correlation between multimodal, like between images and captions. And as long as the language models can understand 3D material structures, then it can be used to discover materials with desired properties. But for sure, there is a major challenge to make large language models understand 3D structures, because language models can only take sequence input in 1D format as input. And to deal with this, we deal with two challenges. First is how to convert crystals into tokens or 1D sequence that language model can understand. And secondly, how to guarantee the uniqueness and the completeness of this 1D representation. The uniqueness means all the different mathematical descriptions for the same structure should have the same 1D sequence. And the completeness means the sequence can fully recover the structure. And here is a pipeline that we convert 3D crystal structures step by step into a 1D sequence that is called map-to-6 sequence that is unique and complete. Before we move forward, let's look at previously used 1D representation for crystal structures, which is CIF. And the question will be, can previous CIF achieve uniqueness or invariance for crystal structures? The answer is actually no. If we shift the periodic boundaries slightly from this point to this point, all the coordinates in the CIF files will change. And even if you use some symmetry control, it will also change. There are some consequences for this kind of not unique, not ununiqueness. For example, you need to inject a lot of intensive data augmentation to help the generative AI or language model to learn that these different sequences correspond to the same crystal structure. And we achieve this by first determining a unique SO3 equivalent cell, and then determining a unique invariant sequence. I will not go into too much details, but here we show the uniqueness verification between our method and previous CIF file-based methods. We can achieve 100% success rate in achieving uniqueness, but others can only achieve 0 or 30%. So here I show some comparisons between other generative AI in material science, like crystal language model, use CF files, or CDVAE and DiffCSP that are diffusion-based models specifically designed for material discovery. We achieved the significant performance gains beyond these methods, even beyond diffusion models, specifically designed for language for materials. And as we can see here, we actually the method can actually rediscover recently experimentally found stable structures with high alignment. And we also verify that metal SiC can generate crystals with desired properties like high bandgap value and low bandgap value with high success rate and uniqueness, validity, and novelty. Here I show some generated crystal structures with high bandgap value. We can see it covers a lot of diverse structures and looks like very stable. Then I will move forward to ongoing and open research directions. First, about language model agents. The reason that we want the language model agents to be in the loop for the discovery of materials is because, again, language models have the richest amount of human knowledge and they can learn the two use with one-shot example. Here are some preliminary results we can share by our efforts. We have established an agent flow for material stable structure discovery with higher success rate for rediscover some stable materials recently found beyond the previous generative AI and also random structure search and evolutionary algorithms. And the number of explorations needed are really limited and very efficient and very cheap. So coming to this, we actually have a complete set of AI tools for crystalline materials for scalars, tensors, dynamics simulations, structure relaxations, and inverse design. What is the next? First, we plan to develop foundation models for general atomic systems, not only for materials, but also for molecules and proteins to study the interaction reaction for the discovery of catalysis, carbon capture materials, drugs, healthcares, and others. We also want to extend the scope from atomic level to other levels for the modeling of complex systems like disordered materials, high entropy alloys, uneven fluid flow under extreme pressure, like speed and others. Yeah, before I move forward, I will answer several questions.
Thank you, Keqiang, for the excellent talk. So, Keqiang, do you want me to read out the questions?
Yeah.
So just make sure everyone have it, and you can focus on the answers. So let me go back to this list. So the next question from Marcus is it possible to predict structure property of materials such as the pore size, pore volume, etc., and or is this energy and forces alone?
Yeah, actually, any general properties, physical properties, as long as you can represent it as scalars, tensors, and other formats, can be predicted by AI methods when it is trained with corresponding labels. You need to have the dataset that contains structures to these properties and then train a corresponding model for this. It is not the ability of AI methods, but what data is available.
Maybe just follow up a little bit for the porous materials. How do you extend your representation to those type of systems?
Actually, the method like the foundation model developed by us is general for any atomic systems. There is no periodic patterns needed. As long as you can construct the local environment by a radius, then it is universal. So I do not see any limitations in this modeling ability of our methods towards other systems.
I see. Another question is, what if we are going to use stack of local interaction to capture long-range interactions? And how do we deal with the issue of smoothing?
Yes, that is an excellent question that actually have several it is the front line of research, I think. We actually have another work to capture the long-range interactions by infinite potential summation, which captures all the two-body interactions in the infinite crystal structure by summing all the potential together. And for the smoothness problem, I think there is not an answer yet, but for sure it's a valuable question to be answered in the research.
The next one asking how to evaluate what physical information different symmetry descriptors captures.
Yeah, so that is an excellent question. To evaluate whether AI model or like a representation or descriptor can satisfy sorts of physical priors, like if you consider the invariance, you can have a structure and construct the representation or like description using the structure, and then apply the transformation that will not change the structure from, for example, shifting the periodic boundaries or whatever transformation that satisfies the physical prior. Then you construct another description or representation and then compare the similarity between these two. If the representation remains unchanged, it satisfies this physical prior. If it changes, then it fails.
I see. So next question, you touched on a little bit, but here talk about the LLM. So besides crystalline structures, can LLMs predict non-crystalline structure materials?
You mean for disordered ones and for like with defects and others, right?
Yeah, I assume, yeah.
Yeah, currently, no. But I feel like it is a promising direction to move forward. This is more like disordered materials are hard to be uniquely described mathematically. You cannot record all the random positions of atoms in the whole disordered materials. So that's why it's challenging.
But still local features, you can still use the same set of rules to represent it.
Yeah. If you
Global.
consider like a disordered ones, like a super large cell, and then you can consider the periodic patterns, then the language model can do that. As long as you consider for example, if you regard disordered materials as a super large cell, but still with periodic patterns, then it can do.
The next question, could you explain a little bit more about how to solve periodic issues when generate new crystal structures? Like how to identify if two crystal structures are the same, if they are different space group with some kind of a transform with nodes and edge models.
Oh, yeah, that's one interesting question to be answered. So actually, the way to compare whether two structures are the same is you need to have a representation that will be the same for these different mathematical descriptions. So actually, you can compare whether two structures are the same using our proposed MAT26 sequence. As long as this sequence is identical, they should be the same.
The next one is, could you talk about more about how you do the data training? How big is the training set? I'm not sure which one is asking.
Yeah, sure. So generally speaking, for property predictions, we deal with the training set with like 60K with labels. And for generation, for these benchmarks, the number of training samples will vary from each other. This will all around the training sets, like several, like 20 to 80K. But for the rediscover evaluation and the property condition generation, The training size will be around 1 million for the structures.
Thank you. So the following question is the sequence encoder that was created to encode crystal information as tokens. Was this a tailored version of word2vec, or was it the basis of the encoding system used to create the special tokens for training?
Yeah, I think they are different. From what I understand, so just make sure I understand the question. Word2vec is it a sequence representation method for proteins that
I,
use
yeah, it is more general word embedding.
oh, so for the embedding of this sequence, we actually use general methods, generally used in language model training. So we do not design any more like a specific embedding layers or whatever. We just map all these char or like symbols into integer and then use the embedding widely used in language models. There is no extra steps.
I see. So could you explain a little bit more about your material agent workflow? Interesting.
Okay. So honestly speaking, I cannot share too much details because this is ongoing. So we actually do the stable structure discovery using like language models to suggest some changes in traditional methods, and then to think whether there are some even more efficient ways to find these stable structures by prompting language models and enable it to use like foundation models to predict force, stress, and energy to relax the structure, and also enable it to use some searching tools and others to search the already available stable structures.
Maybe just follow up a little bit, Keqiang. So do you guys use the well-trained open source foundation models for this tuning, or just you start from scratch?
For the generation, for the generative AI, right?
Yeah.
For this, we train from scratch because as academic model, we cannot support the fine tuning of cutting edge language models. They are like too expensive.
I see. So another question is what make a LLM agent unique, and why can they significantly improve the efficiency of material discovery compared with Gen AI? Is this because of increased automation in your workflow?
Yeah, I feel like the major difference is different perspectives of these methods. Generative AI can like it's more like a mapping from random noise to a known data distribution. You can think about there are different ways, like different passes to a given city. You can take different passes, and there are some limitations and advantages of different passes. So from what I understand, the reason that AI agents and agent workflow can boost this kind of performance is because other methods once developed, there are no like human knowledge involved, but AI agents can more like reason a little bit during the process to speed up the process.
Thank you. So another question is, I'm wondering how does the model performance change if we include more than 5 item types? Is it going to be challenging if there's more than 5 item type in the system?
5 item types, like for this table or like for which?
I think it's for those representation, purpose the predictive models.
Oh, So for our prediction models, we can include whatever number of elements in the system. It will not become even harder, but for sure, if you are asking about performance, the AI model performance will be influenced by the number of training samples in the dataset.
Mm.
And generally speaking, if you consider 5 elements, the training samples will be relatively limited. It is relatively like under-trained, but this is not a limitation of the model, but more like limitation in the data.
Yeah, the next question is long. You have more than one questions. Maybe the first one is how do you ensure that the LLM generates robust and reliable numerical results, such as lattice constant, without introducing randomness or making arbitrary guesses?
Oh, this is really challenging one. And actually, I do not believe language models can directly predict scalar properties, as you mentioned. So language models are like stochastic modeling process instead of deterministic. It is not like DFT or AI methods I mentioned before. So it is very hard to do the prediction like scalar ones.
And then the following question is, do you incorporate any physics-informed constraints or external databases to enhance accuracy in your AI workflow?
So for the just to make sure I understand the question, this is more like do I incorporate external data support with symmetry to enhance the AI model's performance?
Yeah, any kind of physical constraints.
Oh, physical constraints. So for the development of GMT-net, we use intrinsic symmetries as I marked here, R1, R2, to all the RS within the space group. Yeah, that's yes. And for the foundation model, there is no such information used in the pipeline.
But row information is sort of in your encoding or in your tokens representation, the symmetry and rows
Yeah. And for the
information.
generative model, yes. For the generative model, we include a space group symbol, and also like a number of duplicates due to the space group symmetry for given sites.
Yeah, maybe I just want to go back this one. Do you try other fine-tuning approach for this general AI?
Generative AI, right?
Yeah.
As I mentioned before, we cannot support the fine-tuning of open source large language models trained on the like human knowledge or human test. We only have several A100 cards, so that's why.
Yeah. So next question is, could you please go back to the slide that summarizes the tools used? I think it's slide 54. So these two are very useful. Could you provide a more detailed introduction to them?
54.
54, that's what's referred to.
Yeah, for sure. So as I mentioned before, the first part about my talk is the conformer, which is geometrically complete and can distinguish any different structures and achieve all this kind of invariance, equivariance for predictions, including scalars and forces and stress. So it is called conformer. We published it last year in SARR. And for the tensor property prediction, we propose the GMT-net. It can predict order 2, 3, 4, 5, and even more like as long as you slightly adjust the prediction head. It can support general tensor property predictions and satisfy equivariance and space group constraints. And for the materials foundation model, it is ongoing effort. We just submitted it to archive, and I think the code may be released within months. And for the generative AI about Mat2Seq, we published it last year in Europe, and the code is available for try. with the training code provided. So whatever you want to try, just go to our GitHub page, like the AIRS, AIRS. You can like find all these tools within the website.
Thank you. Another question is, what are some of the metrics we can use to validate a machine learning potential for a very large system, which is computationally impossible to obtain its ground truth?
Yeah, this is like very challenging. It is more like evaluating the performance without ground truth, and there are some physics rules actually you can use. For example, the energy of this system should be lower for more like physics. You can sense maybe a given system is more stable than another one. Maybe the energy should be lower. By using sort of like high level ideas, maybe you can draw some ordering matrices when you perturb the structure slightly or whatever. But generally speaking, evaluating the performance without ground truth is very challenging.
Could we use any kind of uncertainty quantification techniques to help?
Yeah, I think, yeah, that's for sure. Yeah, you can inject the uncertainty prediction during training of your model and then use the uncertainty predictions as evaluation for whether the prediction is accurate or not.
Yeah, because this great question is also common in the in catalysis, many other applications. Sometimes you have a really large system that you cannot really use the FT to go back, put back to the FT and reevaluate.
Another thought for this is more like you can do the subsampling of the super large system and then do the support of the structure for DFT and then evaluate the performance of AI.
Hope to see you guys next time.
Yeah.
Bye bye.